Okay, I think. Okay. Oops, what did I do? Okay, so there you go. I'll just turn on my laser pointer. Yes. Great. So again, thank you, Nima, for having me here. And yeah, so today I'll be talking about some of the research that we have been doing on merging or thinking about algorithms as well as hardware architectures that are inspired from the brain or that have some abstractions from neuroscience that can help us build a more sustainable and ubiquitous intelligence as we go into the era of large language models or foundation models. So we are all aware of the recent breakthroughs in AI, whether it is the AI tools today doing video generation tasks that were unfeasible and unimaginable a couple of years ago, to now AI being embedded in almost every technology that surrounds us. We see that, like, there's a massive power of AI, and rightly so. The World Economic Forum in 2024 announced that AI, particularly generative AI, promises to be the steam engine of the fourth industrial revolution. But what has fueled this steam engine are these very unsustainable scaling laws. And what do these scaling laws say? That bigger the models become, the better they are. So as you can see from this plot, what I'm showing you is the growth of models in terms of their parameter count over the years. And what we see is that in case of convolutional networks, which were growing at a rate of 14x every 2 years. And convolutional networks are actually a predominant workload 5, 6 years ago. But as soon as transformers came in, and of course, transformers led to the birth of the chat GPTs today, the growth has been massive. So these transformer-like models are growing at a rate of almost 410x every 2 years. And if you look at your standard DRAM memory, which is your off-chip memory on any commercial accelerator or hardware that is out there today, that is still following the Moore's law trend of the DRAM memory capacity growing at a rate of 2x every 2 years. So Gordon Moore, if you look back, to who is considered to be the father of the computing that we see today, he had predicted the Moore's law, and he had given a seminal speech in ISSCC 2003, saying that no exponential can continue forever, but forever can be delayed. And what Gordon Moore was referring to when he was saying that forever can be delayed, it was basically that with the help of Moore's law, we can always meet the demands of computing of a given era. But delaying an exponential scaling of the rate of 410x every 2 years is not going to be feasible for long with just standalone hardware optimization. So we really need to start rethinking the way we approach AI algorithms, and also start leveraging hardware software co-design in a more integrated and tight loop manner as we design the next generation of AI accelerators. So we know that, like, there is an existential proof out there in nature that intelligence can be achieved in a sustainable and in a low power manner, and which basically this existential proof is the human brain. And whatever little we know of the brain today, even neuroscientists today are trying to figure out what makes the brain so efficient. We know for a fact that the brain operates within a power budget of 20 to 30 watts. And there are a few key things as a hardware engineer that I get inspired by. And what are those few key things? The first and most important thing is that if you look at the brain's hardware and what are the fundamental elements in the brain's hardware, it is the neurons and the synapses. And the neurons can be thought of as the computing elements of the brain, and the synapses can be thought of as the memory elements in the brain. So these are all actually co-located, meaning it's not like the memory and the compute is separate with a wire running between them, which is how today's von Neumann machines are. It's a co-located structure, which makes it very efficient. The other thing is that two neurons, these two computing elements in the brain, they communicate in an extremely sparse and an event-driven manner. So it is these spike-driven computation and communication that allows the brain also to be massively efficient. And the last most important thing, which is still something that is under research and it is under exploration, is that the way information is encoded in the brain. When I see things at the retina itself, there's a lot of processing happening to what the visual stimuli that I receive. And then by the time the retinal processing data goes back to my visual cortex, there's a layers of processing happening. So how is that processing happening? How is the information encoded? All of that plays a massive role in terms of making the brain efficient and capable. And one thing that has become very, very relevant today is that definitely there is a role that timing plays in the brain's encoding of information, meaning that it's not just the spatial relationship between data, but when the data comes and how when the neurons fire in the brain or when the neurons spike in the brain, that is what carries information. So time is really of the essence. So what we have been doing in our group is essentially to bridge the gap between AI and the human brain. We have been trying to essentially incorporate some of these abstractions around a better way of neuronal encoding by bringing in temporal information in a more explicit manner. Looking into different types of algorithms, whether it is from a connectivity perspective, whether it is from a learning perspective, and then, of course, looking into different types of hardware architectures and building an integrated system out of it to understand the viability and feasibility of the techniques that we are proposing is something that we've been looking into in our group. So again, under this broader umbrella of tackling efficiency, we've been looking at encoding, algorithms, and hardware. Just to give you an idea about the type of encoding that we've been thinking about is not just brain-inspired spike-based encoding, where we use this spiking-based leaky integrated fire neurons or LIF neurons, and I'll be going into details of this particular encoding structure in a few slides. But we've been also thinking about low precision computation. So instead of looking at a neuron as a floating point, if you quantize the neuron, then what kind of facets or what kind of capabilities can come through? What is the accuracy efficiency trade-off that we have to manage? All of this becomes important for us. From the algorithmic perspective, again, thinking about connectivity is very important. Should we always go for feed-forward connections, or can feedback play a role? Thinking about hybrid structures of these spiking neurons with the standard floating point neurons, will that give you some interesting capabilities? And of course, like, mixing convolutional and attention-based operations together and thinking about, like, what type of new architectures can emerge from there. Finally, on the hardware perspective, while we've been looking at standard near memory computing and ASIC and FPGA implementations of our new co-design solutions. One thing that is very, very close to our heart, and as one thing that we've been focusing on quite significantly, is how emerging memory substrates based on these in-memory computing architectures can be useful to accelerate these spike-based, these neuro-inspired workloads. And that is something I'll be again focusing on during my talk today. So when I say that we are tackling efficiency, we are not just tackling efficiency at the systems level, but we are going all the way to the top level of the stack, which is the sensors, then managing the software, then managing the systems. And in terms of the type of applications we've been looking at so far, it's both in the vision domain, where you've been, let's say, doing simple classification, segmentation type tasks, as well as in the language processing domain, where, it's all about doing reasoning, question and answering, etc. And with algorithms and hardware, as I have already pointed out, it is very, very important to leverage co-design. And during this talk, I will give you more nuanced pointers as to where exactly co-design can be leveraged and how the algorithms are getting modified or how the hardware is getting modified to fit to the underlying substrate, whether it is the hardware substrate, or to fit to the underlying workload, which is the algorithmic workload. better. So with this overall picture in mind, let me give you a quick overview of the kind of research we do in our lab today. Broadly, the research in our lab can be categorized into three main pillars. The first pillar is basically thinking about scalable spike-based machine intelligence, where we have been looking at new learning algorithms and different types of hardware to benchmarking tools and accelerators that will allow us to implement these new types of spiking workloads, and as well as benchmark them and figure out how they are more feasible and an alternative workload as in terms of energy efficiency and accuracy as compared to standard AI workloads. While we are doing that, we've been also thinking about, now that we have this interesting experience with working with spike-based binary precision workloads, we've been really thinking about what type of systematic hardware design and efficient ML techniques can we implement on the standard and the conventional AI workload part that will allow us to leverage efficiency in a more structured manner. And the main idea behind exploring efficiency is essentially to make AI ubiquitous. And when we think about ubiquitous AI, it's not just for server scale applications where power and memory, these are not really of a big challenge. But what we are really trying to think about is how to drive new edge AI applications, especially for autonomous tasks, where the bot or the AI agent has to be in continuous communication with the human. So what type of new applications can you drive using these low power and efficient spike-based or alternative efficient ML-based techniques is something that we've been driving. So in the interest of time today, I will be focusing on the spike-based approaches. If there is a little time at the end, maybe I can go into the systematic hardware design that we have been looking at, but at least I want to focus on the spike-based approaches in the larger part of the talk today. So before I go ahead, I think this audience might be already a little bit familiar with spiking workloads. Having said that, I just want to give you a quick idea about what are the key features that make spiking a much more efficient alternative than a standard artificial neural network. So I'm going to be using that abbreviation or terminology. A spiking neural network will be referred to as an SNN, and a standard neural network, which uses, let's say, non-spiking neurons like a ReLU neuron, etc., will be known as an artificial neural network or an ANN. It's just a terminology that I use. Now, if you see from the ANN versus SNN perspective, the connectivity between an SNN and ANN can be the same. It can be a convnet. Here, I'm showing you a fully connected structure. What is different is that now, instead of working with real valued inputs, here you're working with inputs that are coming in as a spike stream. And wherever you see these red lines, that means it's a 1. That means that whenever there's a spike, it will be interpreted as a value of 1. And when there is no spike, it will be interpreted as a value of 0. So you have this stream of 1s and 0s essentially coming in. Now, all these stream of 1s and 0s then go through a dot product operation with the help of the weights. And what we see is that then they have to go through a non-linearity. In case of an ANN, the non-linearity that we use, let's say, is the ReLU. But in case of an SNN, now that inputs are coming in over a period of time, you need a non-linearity that has this temporal processing capability. So what we use is a leaky integrate and fire non-linearity. And what is this leaky integrate fire non-linearity? It has this kind of a membrane potential, which is a kind of a recurrent quantity. The membrane potential integrates or leaks in the presence or absence of the incoming spikes. And whenever the membrane potential crosses a certain threshold, it will output a spike. So that is a standard functionality of a LIF or a leak integrate fire neuron. Now, what is the advantage of using this kind of a functionality is that firstly, we are able to now incorporate spatio-temporal encoding at the neuronal level itself because of the fact that we are doing this spike stream processing in this temporal manner using the leaky integrate fire neuron equation. The other thing is that all these neurons, it turns out that they're not going to be spiking at all times. Most of the time in the vision workloads or in the language processing workloads that we have been implementing so far, we see that these neurons have activation sparsity of as high as 90 to 95%. So only 5 to 10% of your entire neurons in your network are going to spike, and the rest of them will be idle. So there's a lot of power efficiency you can extract there. The next thing is that from power efficiency, because of the idleness, we also find that given that now you'll be working with binary inputs and maybe multi-precision weights, your MAC operation gets reduced to a simple ACK operation. So meaning a multiplier and an accumulate will get reduced to a simple and an accumulate, and that means you're really doing multiplier less computations, and that again gives you this fundamental benefit at the processing unit level to implement very low power and energy efficient edge AI applications, because you're completely getting rid of the multiplier in this case. So, as I said earlier, that with these bio-inspired and low-power workloads, the idea is to target edge applications. And what type of edge applications will be very useful for us? Those applications where the data has a temporal blueprint, because ultimately in these spiking models, as we saw, the information is being processed in a temporal manner. So having temporal data will be actually a good marriage between the workload and the application itself. So in that domain, we've been looking into, let's say, AR/VR applications where object tracking is one of the key tasks, autonomous driving based LiDAR based detection, wearable sensor based data, where, that is something has become very, very important in our lab. We work with the Yale Medical School that collect these data from these physical devices like watches, etc., and that allows us to understand behavior of a person who is physically challenged, and maybe we try to collect that data and to see whether a person is going to fall, and if you can predict that fall a little ahead of time, then we can actually have some kind of compensatory and error control feedback to avoid that fall. So that's again something that is very important for us. And then again, we can use these models for planning and control, especially for drone based tasks. Now, these are the skew of applications that we've been looking at. But at the same time, the kind of architectures that we have developed over the past couple of years, it started with convolutional architecture-based spiking neural networks, primarily for vision. But as transformers have become a very important and predominant workload today, so we started really rethinking about in the past 2 years as to how to make a spike-based transformer architecture, and is there actually going to be an advantage if we bring in spiking to this attention operation that I'm showing you here, right? And it turns out that when we looked at it, and this is something that we just recently found out that it's been accepted to ISLPD, that when we looked at the spiking version of transformers, it turns out that the activation sparsity that we see in spiking transformers is much, much higher. And based on that, we have built some accelerators. But the main thing that I want to show you here is that in terms of a spiking transformer architecture, which has this attention operation, and if you see the attention operation, it has these QKV, and then you do this matrix multiplication between queries and keys, and then you will do a softmax essentially, and then do a softmax QK transpose V. So that's a standard attention operation. What we see is that when we do a when we build a spiking based attention encoder architecture, we insert all these LIF neurons in the in-between layers. And because of these insertion of LIF neurons, your intermediate outputs out of Q, K, V, all of these will be binary. And as a result of that, what we find is that your activation sparsity coming from every layer, whether it is a QKV layer or after the projection layer, etc., these are all going to be very high. And just in this graph, I'm comparing the activation sparsity of a standard ANN-based transformer encoder and that of a spiking-based transformer encoder. And we see that the ANN encoder has hardly any sparsity, whereas the spiking encoder has almost sparsity as high as 85%. And the sparsity that I'm talking about is not just dynamic sparsity, where one neuron spikes at this time instant and then it doesn't spike at another time instant. These are this sparsity that I'm talking about is silent sparsity, meaning these neurons are not spiking at any time. So this is how, so silent sparsity is again another form of a structured sparsity that you can induce within a spiking neural network. And I'll be going over that in a little bit later in my slides when I talk about the sparse accelerators that we have developed. But it turns out that this silent neuron sparsity can be really advantageous for accelerator implementation, as well as on a algorithmic level. If you think about it, these neurons are always going to be zero. They'll be always giving you a zero output. So you can do some kind of, kernel development to make sure you don't fetch these activations when you're fetching them from the memory. You can turn off, do some gating if you're doing some circuit implementation. So this is going to be this is going to give you a lot of interesting ways in which algorithmic as well as kernel implementations could be done. Okay, so coming to the main point. So spiking transformers have this advantage of a high activation sparsity. But the other advantage lies in the fact that, firstly, now will be working with all these queries, keys, and values, which are going to be binary in nature. Because of the binarization, again, we don't really need a costly multiplier to do the dot product operation. We can get rid of the multiplier. It becomes a simple mux and accumulate operation. And the most important advantage that we see when we do this spiking based attention is that the softmax unit can be completely eliminated. What is the role of a softmax in an attention operation? If you think about it, it helps you to normalize and take all these negative values and may bring them between 0 and 1. So it turns out that given your query key and values are all between 0, are all binary in nature, so you really don't need a normalization operation like softmax anymore. You can just use a simple non-linearity like a LIF, and that suffices you to normalize as well as get rid of any sort of insignificant values that a softmax would have done. Now, the reason, and today, some of you may have heard that softmax plays a large role today in increasing the latency of an attention operation because they are pretty much sequential in nature. If you think about from a circuit perspective, these are all going to be very complex. They require very heavy exponential computation units, lookup tables, etc. So getting rid of them becomes a very powerful circuit innovation as well. So based on these two advantages, we went ahead and started thinking about what type of algorithmic innovations can we bring in when we develop our spiking transformer architectures such that we can maintain competitive accuracy as compared to state of the art. Now, when we were thinking about developing these spike-based transformer architectures, it turns out we were not the only one. There were other groups also simultaneously thinking about it. But we found out that all the other groups who had developed spiking versions of transformer architectures, they always observed a large accuracy drop. And the accuracy drop I'm quoting here is on the ImageNet dataset as compared to a vision transformer architecture that was always giving the state-of-the-art results. And when we dove deep into why is this accuracy drop happening, we found out that these architectures were really not taking into account the temporal aspect of these models in a useful manner. So firstly, we found out that across different time steps, the spiking features that come in from the query, key, and value inputs are all going to vary. So as you can see from this color chart, we find that across time steps, the QKV information is varying. And what other models or other works did, whether it is a spike former work or a spike driven transformer work, was that when they were doing the attention operation, which is this QK transpose V operation, they were doing it within one time step, meaning that they were taking the queries, keys, and values in one time step and then attending it to each other and then moving to the next time step. So each time step was being handled in an individual manner. So in some way, only spatial correlation was being considered when you were doing the attention operation. Temporal correlation was completely getting mixed. So what we did was a very simple adaptation. And this actually, this paper just will be presented in CVPR next week it got accepted as an oral presentation. So What we started doing, it's a very simple adaptation that we did, was that now that, your queries, keys, and values are all coming in over different time steps. So here I'm just showing you an illustrative example where the same input, let's say input of a cat, has been split into multiple keys and multiple values. And these are all coming in as a spike stream across time steps. What we will do is that we will do a cross attention between keys and values of different time steps. So the keys of earlier time steps or keys of later time steps will be cross-attended with the values of earlier time steps and vice versa. And by doing that, we found out we will be able to get an improvement in accuracy and get this spatiotemporal attention in an integrated manner. The other interesting thing that we also did was that when we were doing this QK transpose B operation, it turns out that now that everything is binary, the order in which we do finally QK transpose B, because the ultimate idea is to get this QK transpose B operation, right? So if we just change the order, that first we do the matrix multiplication between K and V, and then we do the cross attention with Q, it turns out that that allows us to reduce the complexity to linear in n versus quadratic in n complexity. So previous architectures generally had a quadratic in n complexity because they were not really switching the order of operation, and we were able to switch the order of operation. As a result of that, we were also able to get a linear in n complexity. And as you can imagine, like, today when you talk about attention transformers, you hear this word, right? Quadratic attention have quadratic complexity. So the quadratic comes from the n value, where n is the sequence length. It is the token number of tokens that are being processed. So now we can actually make it linear in the sequence length of token. So that is again a very, very powerful thing from the processing perspective that spiking based transformers can give you. So there's a whole lot of potential to think about spike based transformer architectures in the future. So coming to experiments, I've told you what we do. Now let me convince you with the results. So here, what we see firstly is that we are getting state-of-the-art results. It's this spatiotemporal attention module, which we call as statin. It's actually a plug-in module. So we took a lot of previous architectures and we just modified their spatial only attention operation with our spatiotemporal grouping-based attention. And we found out that we were able to now get better accuracy than all those previous architectures, almost 1.93% improvement. What I also want to focus here, one other aspect, is that we are in the top row here. I'm comparing with standard vision transformer architectures, meaning it's all non-spiking based. And what we see is that now we are getting almost similar accuracy as that of a standard vision transformer architecture at lesser parameter count cost. So the standard vision transformer has almost 87 million parameters, whereas our model has 67 million parameters, let's say. But having said that, I just want to say this with a pinch of salt that, if we want to get up to 83 or 84% accuracy, we also have to increase the parameter size. So currently in our group, we are trying to figure out whether or not there is a better way to get accuracy improvement up to 83, but not really increasing the parameter size too much. So that's something there. But still, what I'm telling you here is that initially, this is a very encouraging result that if you bring in spatiotemporal attention, probably you don't have to follow the same rate of scaling law as that of a standard vision-based transformer or an ANN-based transformer, right? Maybe our scaling law will be there, but it will be at a slower rate as compared to a ANN-based transformer. The other thing is that because we were working, so all the data that we worked for this architecture was on the vision domain. So while working with standard static data sets like ImageNet, etc., we also looked into some temporal data sets like the DVS data set. And in DVS data set, again, we found out that the accuracy improvements that we got were higher. We were getting at least 3% higher accuracy than that of the state-of-the-art on DVS data sets. Now, the most important thing I want to then come back to is I motivated spike-based workloads with the reason that I want to tap into energy efficiency. And what we found out is that because statin, this spatiotemporal attention module is a plug-in module, we are basically changing any previous architecture with this spatiotemporal attention, first and foremost thing is that we don't want to add any extra overhead because of doing this grouping and then doing this early versus later cross attention. So it turns out that as compared to the prior architecture on top of which statin was built, there is hardly any overhead. And as compared to ANN based architectures, we get energy efficiency of the order of 20x. So there's a lot of potential for energy efficiency. Now this is all good. So that means that, spiking is going to solve the problem, solve the all world's problems around AI efficiency, right? But it is not as simple because when I told you about this energy efficiency improvement, it turns out that, and this is not just me, there's a lot of groups that today, when especially algorithmic groups who talk about spike-based algorithm design and quote energy efficiency numbers, they generally tend to use the energy efficiency calculation based on this very simple estimate. And this simple estimate, what is it? It's a flops based estimate, right? So you can take the total number of flops you have in your spiking architecture. Then you multiply it with the overall sparsity, meaning that like, how many neurons are finally spiking, because only for those neurons you will estimate the cost. And then you will also multiply it with the total number of time steps for which you have to process the inputs, right? But if you think about it, this is a pretty obfuscated cost, right? You are really not taking into account any memory, data movement, or data flow related costs. So that was something that pinched us when we also started quoting these numbers like 20x and all. So then we started thinking about, no, we need to do it better. So we started really building benchmarking platforms that will allow us to give realistic estimates of energy efficiency, right? Such that we ourselves can guide our algorithms in a way where on realistic hardware, this will be efficient if you can develop the right kind of schemes for it. So with that in mind, we in our group, because when we started thinking about, okay, we need to do benchmarking, it turned out there was not a lot of benchmarking tools available for spiking. So that became a big part of our effort in our group. So we developed two main platforms. One was a simple systolic array architecture based platform, which we called as SATA. It was based on a 32 nanometer CMOS hardware. And the other is called SpikeSim, which is basically an in-memory computing crossbar-based end-to-end evaluation engine. And because this is a MIM webinar, I thought I will focus on the SpikeSim evaluation tool today. And we just got to know like a week ago that this won the Best Paper Award in IEEE TCAT. So we are very excited for it. So SpikeSim basically is an integrated circuit to algorithm benchmarking framework for spiking neural networks on in-memory computing architectures. We support a host of devices from RRAMs to FFH to also SRAM devices. This work firstly was done in collaboration with Professor Kevin Cow, who is at University of Minnesota, who provided us with all these in-memory computing models that he was at that point of time working with Global Foundries. So SpikeSim, if you see, it's a tiled array architecture. It's a pretty simple evaluation tool where you have multiple tiles connected through an NOC. At the tile, if you look inside the tile, then you have this multiple processing engines that are connected using a H tree. Then within every processing engine is this multiple crossbars, and then a crossbar essentially has this analog crossbar architecture with input peripherals and output peripherals. Now, SpikeSim, if you look at the tool itself, what it allows us you to do is that it takes a pre-trained spiking neural network, right? And it will do energy latency area evaluation as well as accuracy evaluation. So what it does is that if when you give it a spiking neural network, it first takes that network and partitions the SNN into different crossbars. So it will give you a layout of how many tiles are required, what is the kind of peripherals that are required based on the precision that you want, etc., etc. Then it will do a floor planning, meaning that it will, based on user-defined parameters like crossbar size, device precision, etc., it will initially initialize the entire SpikeSim based network. And then finally, it will invoke its two internal benchmarking tools, which is the energy latency area tool, which will actually do real-time NOC trace generation, active layer tracking to give you realistic energy latency area results. And then it will also, if you want to also get realistic accuracy, which incorporates non-idealities like read noise and intrinsic parasitics, etc., it will also give you, do a circuit analysis, taking into account quantization, all of that, and give you a hardware realistic inference. So in SpikeSim, this is like the standard ELA engine that we have built. So as you can see here, so after the weights of the model are partitioned into different crossbars, it will go ahead and do the NOC trace generation. We also try to make sure that we are doing a very efficient way of evaluating. It's not like we are making the engine very, very inefficient. So we do some pipeline layer-wise execution to make sure that we are maximally utilizing our crossbars. And that will give you a more optimistic estimate of the energy latency and area. And in terms of the non-ideality evaluation engine, again, the idea is that we are taking into account different types of, depending upon the type of device we have, we incorporate the device read noise, we incorporate the cycle-to-cycle variations, circuit parasitics like IR drop, row parallelism, all of that is being accounted for. At the same time, we also recommend, in the tool, it recommends that, if you want to do some calibration on the trained model to incorporate all these non-idealities and mitigate them. So it will give you some batch norm adaptation based statistics and calibration capabilities that will allow it to resist against non-idealities also. But if you don't want to incorporate that, that's fine. It will give you a whatever is the hardware realistic accuracy. So going into the quick results, so SpikeSim, that was the basic behavior, overall implementation of SpikeSim, but going into the basic results that allowed us to then think about what are the kind of co-design, what are the kind of algorithm changes that I need to do going forward, because I was not too happy with this 20x energy efficiency, as I told you earlier. So that's why I went for a realistic estimate. And from realistic estimate, we will start modifying our algorithms from there. So first and foremost, when we did the energy and area cost breakdown of a spiking neural network, and this was a simple VGG-like spiking neural network I took and estimated it on SpikeSim. Firstly, we find that, as we all know, digital peripherals dominate the total energy and area cost. The most important thing is that the LIF area, because my leaky integrate fire neuronal module is actually being implemented in a digital manner. So that accounts for almost 30% of the total area. And because the membrane potential is kind of like a recurrent quantity that needs to be stored, so there's a large SRAM cache in your digital module, and that accounts for a large area as well as a large energy. The other interesting thing we found out also is that in case of a spiking network, it uses a flash ADC because we are optimizing for latency over area in this case. The interesting thing that we found out was that the precision of the ADC required when we are implementing a spiking neural network is slightly lower than that of the precision required for a standard artificial neural network. And why is that so? Because your inputs are going to be binary and sparse. So the partial sum output that you will get, the overall value that you will get is going to be of a lower range. So 4-bit ADC is going to suffice. So here the peripheral cost in general, just because of the ADC, will be lower. The other thing we also found out, besides, so LIF cost is higher, peripheral ADC cost will be lower because you can have lower precision ADC. The most important thing we found out is that it is the time steps that completely determine your total energy and latency. So the number of times you process the input, that is going to have a linear relationship with your net energy and your net latency. And it turns out that if I just reduce the number of time steps, let's say, my algorithm tells me that I need 5 or 6 time steps to get the best accuracy. But if I just reduce the number of time steps to 2, let's say, then you see a sharp drop in accuracy as well, right? So there is this big time step related factor that I need to start minimizing, or I need to start developing my algorithm around such that it doesn't impose a huge energy latency bottleneck. So what we then decided was that we need to start decreasing the time steps, but we cannot decrease it uniformly across all inputs. So can we dynamically vary the number of time steps for different types of input? And in this case, the idea was that given that in a real world data set, not all inputs are going to be the same, some inputs might be more difficult than the rest. So can we use lesser time steps for what we call as the easier inputs? And can we use more time steps for what we will refer to as the difficult inputs? So in this example here, both are examples of chairs, right? But if you see the bottom figure, these chairs look like eggshells. So unless you really look deep and see that, oh, this is probably in some coffee shop because it's in a building. So this looks, even though these chairs look like an eggshell, they're actually chairs. So essentially, there will be many such examples in a real world data set, and you want to take advantage of that variability in your inputs to dynamically toggle the number of time steps that you require. So what we did was that in this paper, we developed what we call as a dynamic time step SNN. And the main idea was that we start adjusting the number of time steps required by a spiking neural network during inference based on the difficulty of input samples. And the way we decided this, whether how many time steps are required, is using a very simple confidence thresholding mechanism. Meaning that, let's say one input comes in for the first time step, at the output, we measure what we call as the confidence score. If the confidence score is good enough, we will go ahead and exit the inference at that time step. If it is not good enough, then we will go ahead and iterate the input for the next time step. It's a very simple technique. And what we found out was that we actually went ahead and implemented this version of a digital confidence thresholding unit, integrated it with SpikeSim architecture. So in real time, during inference on SpikeSim, our SNN can do this dynamic toggling based on the input coming in. And turns out that this thresholding unit that we implemented, this confidence thresholding unit that we implemented on SpikeSim, was actually a digital module. This was nothing, because it's a simple LUT-based thresholding that we did. So the energy of this digital module was actually negligible as compared to the total energy of the IMC architecture. So what I want to show you here is the main results. And the main results, so this is a pretty populated graph. It has a lot of information. So let me go over one of the graphs. So I'm showing you the accuracy versus energy delay product, comparing my dynamic time step SNN versus a standard SNN. When I say a standard SNN, meaning that I don't toggle the time steps. I use the specified number of time steps for all inputs. Whereas in a dynamic time step SNN, I vary the number of time steps based on the confidence thresholding procedure. First and foremost, we find that the accuracy is much higher with a dynamic time step SNN, right? And we are also getting almost 81% reduction in our energy delay product. This is all evaluated on SpikeSim. So the accuracy being higher tells us that actually toggling the time steps is probably better because it allows you some generalization capability. Maybe when we use specified number of time steps for all inputs, it might be that you are going into some kind of a overfitting region, and by toggling the time steps, you are doing generalization or regularization. The other things inside, if you see here in this pie chart, what I'm showing is the fraction of inputs that are classified at different time steps. And what we see is that almost more than 90% of your inputs, which are shown by this yellow and orange portions here, more than 90% of the inputs are actually being classified at the early time steps, which is t equal to 1, t equal to 2, meaning that across your real world data set, most of your inputs can be deemed to be easy, right? So only for fraction of inputs, 10% of your inputs, you really need larger number of time steps. So it is a complete waste of your total energy, latency, and area if you use the specified number of time steps to maintain the accuracy. So that was one thing. I also want to kind of bring your notice to this paper. If you are very interested in thinking about how spiking neural networks and in-memory computing architectures, what is the kind of opportunities that lie there? What are the type of core design challenges that are there? So we actually published a applied physics review paper at the end of last year, and that gives you a very good analysis of what type of considerations one needs to make. And it also gives you a lot of interesting ideas about, from the device perspective, what are some of the challenges that we need to think about when we are designing new algorithms for these emerging workloads. Okay, so besides doing a very simple toggling where I just dynamically toggle the time steps. I could also go for very standard and compression techniques, right? Quantization is one of them, because when I quantize my model, I will be able to reduce the number of crossbars, let's say, my ADC precision would further be reduced. If I'm quantizing not only the weights, but also the membrane potentials, then my leaky integrate fire neurons area will be reduced because I don't need a big SRAM, etc., etc. Similarly, I can do pruning also. So I can make a network more sparse as a result of that. And both activation sparsity combined with weight sparsity can be further helpful. I can do sharing. And this is a work where we're looking at, like, can one layer's membrane potential recurrent processing be shared with later layers membrane potential recurrent processing. So that can be also useful as we are thinking about reducing the costs. And of course, as I said, dynamic time step is a very simple and a very effective method, as we saw earlier. Now, I talked about how to reduce the ops part in some way, right? By reducing time steps, etc. The next thing I want to talk about is to when we are doing this algorithmic estimation of efficiency, when I told you 20x, we are also taking into account sparsity into the picture. And when I say sparsity, it means that if a neuron doesn't spike, I am thinking it will not have any memory related cost. I'm thinking it will have not have any compute related cost as as an algorithm designer. But we know, as on the hardware, sometimes the zeros have to be fetched also, right? So sparsity that is considered here is unary sparsity, right? And leveraging unary sparsity at the hardware level is actually extremely challenging, right? So what I'm showing you here is, let's say this is a standard sparse spike matrix that you get. You have this kind of a spatial and temporal dimension of the matrix. And when a neuron doesn't spike, what you can do, what we generally tend to think about is these sparse spikes will help us reduce the total number of computations. So let's say that you have this input spike train 001, 001. In this case, if you think about it, I can gate off my computation whenever a zero comes in. That means the number of computations I will do is 3, but I will still have to use my processing engine 6 times, right? Because it's a 6 time step spike train. So sparse spikes can help reduce the number of computations, but not the overall latency. Now, what you can tell me is that, no, I'm going to now reduce the latency. And the way I will do that is I will store my spikes in a compressed form, right? So instead of storing my spike as 001, 011, I will store them as 111, where I will have value matrix and an index matrix that will tell me that where exactly are these spikes occurring, right? So that means now I have reduced the number of computations and reduced the number of processing engine cycles. But to store this spike train in a compressed manner, so in some way I'm using 3-bit index values to compress 3 bits of data. So your compression efficiency is going to be very, very low. And this is not a good idea then, right? So the question is that leveraging unary sparsity on a hardware is absolutely not going to give you any benefit, right? No matter how high sparsity you have. So what we need to leverage, now let me remind you of that silent neuron that I talked to you about. In spiking transformers, we see these neurons that are not spiking at any time step. That's what we will leverage now. So leveraging silent neuron sparsity for acceleration will be helpful to us. So what we do is that we take these neurons that are not spiking at any particular time step. So you see that, these are 2 neurons here, index 1 and index 2, that are zeros at all times. So we will take them and we will now do the compression along the temporal dimension. So that means we will do the packing along the temporal dimension. And now if I do this silent neuron based packing and compression, we find that now the compression efficiency is actually going to be more than 1, right? Which is what is always required when you're doing any compress sparse formatting. And turns out, as I said, why we are able to still get a higher compression efficiency with these silent neurons, because the amount of silent neurons that we see in traditional workloads is of the order of 80%, right? So this is something that you should leverage. The final thing you should leverage also when we build these accelerators that can leverage sparsity is that you need to make sure that there is an aspect of timing. Like, while we were able to reduce the total number of time steps required to process an input that was algorithmically induced, but from the hardware perspective also, maybe you can do something to make the sequential processing across time more semi-parallel, let's say, right? So what we did was that you can come up with a new data flow, and this is something we did with our accelerator that I will talk to you about, where we try to reduce this expensive data movement across the temporal dimension. And so rather than having this for loop across t times, where everything, your M and K computations will be repeated t times, we tried to see that can we come up with a more parallel version of this for loop. And again, I'm not going into the details of what is the parallel for t loop that we did, but one other thing we did was that when we are deploying this MNK workflow in our systolic array architecture or any kind of architecture, it's important to make sure that the for t loop always remains in the innermost loop, because then this MNK workload becomes independent of time steps. So you're not really moving the MNK values across time. So that will again reduce the data shuttling. So based on these two things, what is leveraging silent neuron sparsity-based compression and using this parallel temporal data flow, we developed what we called as a dual sparse spiking neural network accelerator. We call it LOAS. It was published in Micro 2024. Quickly going over the results because I'm running out of time and I want to use some time for questions. Firstly, we found out that, with the help of LOAS, we now have almost 5x reduction in our data traffic. And as compared to prior SNN accelerators, now we are getting 2.8x more energy efficiency, and the speed up that we get, because we are not anymore processing information in a sequential manner, it is a parallel T acceleration that we are doing. Also, we are taking advantage of the silent neurons. So for the silent neurons, there is absolutely no data movement or processing happening. So the speed up that we get as compared to the prior dense SNN accelerators is pretty high. So if you see here, this 2.8x, so from 20x, on realistic measures, this actually becomes 2.8x. So it's very important. So if you think about it, somebody might tell me like, you're kind of not, spiking networks, if you see there's like, people will give you numbers like 50x or 100x, but something that I have been trying to do in our group as well as to the larger community is that we have to build these realistic accelerators, whether it is a spike sim like tool or whether this is a LOAS like tool. We have to build these so that we understand where are the bottlenecks that will allow us to develop the right kind of algorithms for the future, right? So with that, I just want to give you a quick brief of the kind of work that we have done, right? We've developed hardware simulators, we're developing scalable training and inference algorithms, very simple plug-in mechanisms that will allow you to deploy spiking networks on realistic hardware in an efficient manner using dynamic time steps or using quantization. Something that I did not have time to go over is that spiking also has a very, very potential, a very, very large potential to become a more robust and privacy preserving algorithm as compared to standard ANN. So we have some works, theoretically oriented works, where we are showing that with a spiking model, it will be very difficult for you to reverse engineer the model and then thereby do model leakage, etc. So this is something that could be also interesting as we want to build more robust and private models. So to summarize, where and why SNNs are a good alternative. Firstly, energy efficiency is your primary advantage. They are more relevant in the field of edge computing and robotics. The other thing is that models need not be fully spiking, meaning that your data type and modality must dictate when and how spiking neurons should be used. And nowadays, more and more, we've been thinking that spiking should be treated as a feature rather than a backbone. So wherever you can, bringing a spiking inclusion in a standard backbone, maybe you should do that and see if this recurrent processing capability with sparsity will be allowing you to make things more efficient as well as accurate. Spike-based retention mechanisms have a huge advantage, linear and complexity, no softmax requirement. So that is something that would hold promise for embodied applications. And finally, I just want to say that besides ASIC or neuromorphic hardware-centric solutions, it is also important to think about building general-purpose hardware-efficient spiking algorithms, meaning that we need to now start thinking about how to reorient our GPU kernels, whether by building in QPy support or some kind of a CUDA support, to train these models, especially spike-based or hybrid models, faster, and then try to see what type of efficiency advantages we can get. So that is also very, very important. And that's important because we want to, that will give us a big push towards propagating spike-based AI into multiple applications. So with this, I would like to just thank you all for your attention and open the floor to some questions.